Hello everyone, so let's talk about SN2. SN2 is one of the main reactions that you're going to be seeing in organic chemistry. It's a very important reaction, and so I wanted to talk about the mechanism and how it works. Well, first of all, the features, and then the mechanisms. That way you guys can see the differences between SN1 and SN2. For you to really appreciate the difference between SN1 and SN2, please go check out my SN1 video where I talk about all the SN1 key features, so that way you're going to be able to see and note the difference, because there is a difference in mechanism and how it operates. So without further ado, let's talk about SN2. So SN2 is again another type of substitution reaction, but the key features are as followed. It's a concerted reaction, meaning it's one step. It prefers a primary substrate, unlike SN1 that prefers a tertiary substrate. There's an inversion of the configuration. In SN2, you're not making any enantiomers. What you're doing is, you're not making a pair of enantiomers. What you're doing in SN2 is that you're going to invert the configuration. So if you're going from you have a bold, it's going to become dash. If you have a dash, it's going to become bold. But you're not switching the whole molecule. If that was too much at one time, don't worry. I have examples at the end, and I'm going to emphasize it. Okay, you don't need a strong leaving group, like a very excellent leaving group is what I mean. You can have an okay leaving group. And again, you need a very strong nucleophile, so preferentially a strong base. And again, one point that I want to make about strong bases is that when you see strong bases, usually you see E2 reactions as well. And so what I want to tell students is that sometimes I know that when I was going into it, I was thought, oh, this is only going to have an SN1, or this is only going to have an SN2. But SN1 and E1 can occur at the same time. Likewise, SN2, E2 can also occur at the same time in solution. And so these reactions are not separate from one another. But what I don't want you to do is be scared and be like, oh no, then what do I do? Your professor will tell you, give me the substitution product, or give me the elimination product, or give me both products. But what you need to know and be the Sherlock Holmes and differentiate and say, what would happen in this reaction? Like, if I'm going to have a substitution reaction, is it going to be SN1 or is it going to be SN2? Do I have a primary? Do I have a secondary? Do I have a tertiary substrate? Do I have an excellent leaving group or an okay leaving group? Do I have a strong nucleophile or a weak nucleophile? Do I have a polar protic solvent or a polar aprotic solvent? And from there, gauge and determine, okay, well, I have a tertiary, I have a weak nucleophile, I don't have a strong base, I have a weak base, I have a polar protic, it's probably going to be a SN1, okay? See what I did there? So what you need to do is gauge and determine. Likewise, you can do the same for SN2. Oh, I have a primary, I have a strong base, I have an okay leaving group, I have a polar aprotic solvent. This is probably going to be an SN2. The same for E1 and E2. You can gauge, do I have a weak base, do I have a strong base? And again, you need to be the Sherlock Holmes. So now that I've discussed that, quick note, SN2, it prefers a polar aprotic solvent. If you think about it, it's concerted, it's one step. It doesn't want anything to interfere. And polar protic will slow down the reaction. Okay, so at this point of the video, I haven't even discussed the 2. What does the 2 stand for? So it refers to the kinetics, and this reaction is bimolecular. Unlike SN1, it is bimolecular, meaning it's going to depend both on the substrate and the nucleophile. So that's all I'm going to discuss for the kinetics of these reactions. If you need me to go into depth, I can definitely make another video on that, so please let me know in the comments. So now let's get into the actual mechanism of SN2. So in this first reaction, as you can see, I left the note that there's going to be no stereochemistry because there's no stereogenic center. Again, if you look at the carbon that the bromine is attached to, 2 hydrogens are also attached. Again, you have 2 of the same group. Therefore, you do not have 4 different groups. Therefore, you have no stereogenic center, and therefore the molecule is not chiral. So for the mechanism, the hydroxide, the oxygen is going to go and attack the carbon, and then the bromine is going to leave, and you're going to produce an alcohol. Now, something I want to address is that some students, when they ask me about the mechanism and I show them, they ask me, why does the oxygen attack the carbon? And just to give a short, quick explanation, is that if you look at electronegativity, if you looked at when you go to the periodic table, fluorine is the most electronegative element in the periodic table, and oxygen is very close. So oxygen is more electronegative than carbon. Also, you would need to think about opposites attract, right? So those electrons are attracted, they're negative, they're attracted to that positive. So those electrons are attracted to that positive carbon. The other thing that's influencing the positivity of that carbon is you have a bromine there. So bromine is pulling those electrons away from that carbon because, again, bromine is also electronegative and it wants those electrons. So that makes that carbon even more positive. So it gives it an electropositive density, and therefore those electrons are going to go and attack that carbon. But again, carbon can only have 4 bonds, which is why bromine has to leave. If bromine didn't leave, there would be 5 bonds, and that can't happen because, again, carbon can only have 4 bonds. Okay, so let's go into the next example. So again, you have your acetonitrile, you have a carbon ion with that because the carbon is negative. It's going to go and attack the other carbon, then the bromine's going to leave, and again, you produce this product. Now, a common mistake I see with students is that they're going to put the alkyne all bent over, and that's not going to happen. It doesn't function like an alkene. Alkyne is completely straight. It's 180 degrees. It's as straight as you can get. So I'll make a separate video on alkynes, but just be aware and cautious of that because you will get points taken off. Okay, for these next 2 examples, I know you're like, well, isn't that the same? No, because if you can see on the other carbon, one is bold on the top example and the other one is in dash on the bottom example. And what I wanted to show you with this is that some students think that whenever you're doing an inversion of the configuration, you're flipping the stereochemistry of the whole molecule, and that is not true. What you're doing is you're changing the configuration only of the carbon that you are attacking. So again, to give you the example, oxygen is going to attack here, and the bromine is going to leave, and that bold bromine became a dash OH. So the bromine left, and you replaced with an OH, but that bold becomes a dash. So some people think of it as the backstabber because you're changing from bold to dash or from dash to bold. Like you're giving a double face. Okay, you have to make chemistry funny, right? So if you think about it that way, you're not changing the other configuration. You're not changing the other stereogenic center. You're not touching that whatsoever. You're only touching what you are attacking. To emphasize this example, I'm going to leave the dash alone, right? And again, I'm only changing that bromine that was in dash is now, the bromine in bold is now going to be the OH in dash. And again, the OH attacked, the bromine left, and again, OH replaced that bromine, but it's no longer going to be in bold, it's going to be in dash. And that's what SN2 is known for, and that is what inversion of the configuration means. This last example, you have OCH3 is negative, it's going to go and attack, the bromine's going to leave, and there you're going to have your product. I didn't go into depth, but notice one of them had acetone, the other one had DMSO, and again, those are polar aprotic. So again, I'll make a separate video on solvents. And the other thing I wanted to show you is just that even though that SN2 prefers primary, it doesn't mean that it is not going to occur with secondary. So again, this carbon, wrong one. This carbon here is attached to 2 carbons, so this is the secondary. This one is attached to 2 carbons, so this is a secondary. I wanted you to be mindful of that because some people think, oh, it's only going to be with a primary substrate. And no, that's not the case. You have to look again. Do you have a strong nucleophile? Do you have an okay leaving group? Do you have an aprotic solvent? Again, you need to be the Sherlock Holmes. Again, if you enjoyed this video, please follow, like, share. It takes time to create this content, and I want to reach and help as many students as possible. I know that OChem is a very grueling subject for a lot of students, and so I definitely want to help and show you the tips and tricks that I learned to get an A in OChem 1 and in OChem 2. So thanks again for watching, and happy studying.